Hello, I'm going to describe the project that I'm currently working on, and it involves developing machine learning system for identifying false calls versus real defects in the environment of automated optical inspection. So the main requirement is that images that were found by AOI, stands for Automated Optical Inspection System, has to be classified as either defects or false calls. And the goal is to filter out most false calls while keeping escapes to the minimum. And by escapes, we mean real defects that were classified as false calls and as a result escaped to the final product. And on the right, there are examples of this type of images that would represent some type of false call, like foreign material or some type of dust. And this is the short that is a critical defect and has to be detected. Is there a problem? There's definitely a problem because AOI typically operates in an overkill mode. What it means is that we make AOI as sensitive as possible, so it can detect as many defects as it can. But the downside is that results in more false calls that has to be filtered. Right now, they're filtered manually. Does anyone care? Yes, absolutely. PCB manufacturers do care about this problem because more false calls mean less productivity and also increased number of false calls require more manual verification station and more people to operate them. Can machine learning solve this problem? We believe it can because machine learning is good in image recognition, and that's exactly the type of problem we're dealing with. Business understanding. So the target user here is a PCB manufacturer, which are AOI users, and we are actually manufacturers of this AOI equipment, so we know the business quite well. And the problem here is access of false calls that is affecting production efficiency, but it also increases capital expenditure because customers have to buy more verification systems and also operating expenditure that is all about operating those systems and maintaining them. Classification of defects in AOI process right now is done manually by human operators. So there are people who are sitting in front of live videos and verifying those defects manually. And currently, the only way to reduce false calls from the beginning is to reduce sensitivity of AOI system, which carries risks. If AOI is not sensitive enough, defects will be missed, and this is what customers want to prevent. So in some cases, there's no choice, and system has to be set to maximum sensitivity, but that results in higher rate of false calls. There is definition of success that those definitions vary from customer to customers, but there's agreement about filter rate that should be at minimum of 40%, and of course as much as possible is always good. Escape rate varies depending on customer and specific case from 0.5 to 0.5%. And the outcome metrics include specific requirements for reduction in verification station, which relates to capital expenditure I talked about before, and associated human operators, operating expenditure. And there are constraints. The first one is the level of user cooperation in collecting and classifying defects. Sometimes it's hard to convince operator to do a good enough job. It also affects classification accuracy. If people are sloppy and not used to this type of work, the accuracy of the training data will suffer. So as a result of those type of inaccuracies, we have to reclassify data manually by our own data engineers offsite. And the relevant factors that we also have to consider. First, we have to gather necessary expertise, which we already did, and customers agreed to collect and classify a certain amount of data, and we had to negotiate over how fast it can be collected. And we decided together with the customer to separate projects into different phases. The first will be proof of concept, then development, then internal test using the data that we've collected, then deployment, then we continue testing after deployment, and then we also have to agree on the retraining schedule. The concept is going to look something like this. There are AOI systems that provide real-life data to the server. That's where we keep all the data, and then there's another server that where AI model is sitting on, and it crunches the data at the same time as it comes in, and it classifies data as non-defect, meaning false calls, and those are removed from the verification pool. The other type of data, which are automatically classified as critical defects, like opens and shorts, automatically scrap PCB units, so we don't have to deal with this. And everything that AI system is not sure about, or any defect that can be manually repaired on verification station, would be transferred to verification. So the savings here are the fact that we don't have to deal with the non-defects and critical defects, which are automatically taken out of the pool. Our validation plan includes several stages. First, there's initial validation that is done on collected data. So we set aside about 15% of all the training data that we've collected from the customer in order to run validation tests once the first version of model is completed. Then, depending on the results, we might request more data and run more tests until we reach the metrics that we agreed upon with the customer. And there will be final validation stage to be performed on the customer side after model was deployed and we start receiving real production data. Our design decisions are as follows. We decided to go with the edge model because the decision on the type of defects versus non-defect has to be done quickly, almost immediately after scanning was completed. And there's also security concerns on the part of our customers that do not wish to upload any of their sensitive data to the cloud. Learning has to be done offline. We are collecting batches of data of about 100,000 defects per batch, and then we pass it back to our R&D when our engineers work on improving the model, and then we redeploy updated model on the customer side. And prediction is done online because there's a minimal latency requirement between AOI, which is scanning, and verification. So the prediction has to be done fairly quickly during verification process. And our potential risk in production that we have to realize first one relates to concept drift. The idea here is that the requirements that define defects versus non-defects are constantly changing. So in some cases, certain defects were considered non-critical in the past, and now they are critical defects, so they cannot be filtered out. And the opposite is true. So some non-critical defects are now become critical defects. An example could be a foreign material that is stuck on a trace. When it can be removed, then it's a false call. But if it cannot be removed, it stays on the PCB board and it becomes actually critical defect. So those kind of concepts keep changing. And then there's a data drift. Data drift relates to ratios between critical defects and non-critical defects or false calls that is constantly changing because of different conditions in production, and this affects the data. So we have two types of risks here present, and we have to deal with that. And that's all. Thank you very much.